Okay, so this is problem 10, the last section of the book. So we have our coordinate system, x, y, z. And then we have this parabolic cylinder, something like this. So it's a parabola in the x or the ZYZ plane, and then it continues out. Now the outward normal, I think we're going to say, is this direction. So that means that we need to go this way around the boundary. And in the book they're calling this curve 1, and they're calling this curve 2. So this part is curve 2, and then you've got curve 3, which is the part right here, and then you've got curve 4. So it kind of goes curve 1, curve 4, curve 3, curve 2. So it goes, this starts at the origin, goes to here, which has x equals a, and it goes up to this point. The coordinates of this point are x equals a, y equals a squared, I think. No, x equals a, y equals a, and z equals a squared. And then you come over to this point here, which is x equals 0. It's along the y-axis. X equals 0, and then you'd have y equals a and z equals a squared. And this point here is a comma 0 comma 0. And of course the origin is 0, 0, 0. So it goes from 0, 0, 0 to a 0, 0. Then it goes up here to a, because it's constant value of x. Y value is increased by a. Z is a squared. Then it goes back to x equals 0, but the y and the z values remain constant. And then it goes back down to the origin. So what we're trying to do here is verify Stokes' theorem, which says the integral around a closed curve of f dot ds is equal to the double integral over the surface of the curl of f dotted with n dot dA. So this n is a normal vector, I guess a unit normal vector. So it's this vector here, which is not constant across this integral. The curl, of course, is crossing the delta function, the del function with the field variable. And what we typically do here for the line integral is we take f dot with r prime of t times dt. So we have to parameterize both the field variable and the position vector. So what we're going to do is we'll do this line integral first. And so we're going to go, this is C1, which is from 0, 0, 0 to a 0, 0. So from a parameterization perspective, x is equal to, what is it going to be? Well, let's let t, what is t going to go between? If we go between 0 and 1, where a is equal to, x is equal to a times t, and y is equal to 0, and z is equal to 0. So you can see when t equals 0, you get x equals 0. When t equals 1, you get x equals a. So let's go back over here and write what for this particular problem, the field vector is given by, what is this thing given by? So there it is, z squared I plus x squared j plus y squared k. And this surface is this parabolic cylinder. Okay, so if we wanted to write the field vector along this particular curve of x, y, z, but in this case, you know, y and z are 0. So this goes to 0, this goes to 0, and you have, so you'd have x squared j, the only term that's left, but what we do is we then plug in at for, so it's at quantity squared j. So that's the field vector. In terms of the parameter t, the position vector, as a function of x, y, and z, is just going to be ati plus 0j plus 0k, and the derivative of this with respect to t is just ai. These are 0, so the derivative is 0. And then when you do the dot product, so if you take f dot r prime of t, you get 0, because you see here there's no I component, and here there's no j component. So we get that for this first curve, that the integral, the line integral, so we'd integrate from t equals 0 to 1 of f dot r prime of t dt is 0, because this dot product is 0. Okay, let's do curve 4 next. So curve 4 goes from, so curve 4, so that goes from a, so it goes from a squared, oh no it doesn't, it goes from a0 0 to a squared. So you can see that x is just a constant a. Now y, let's let t go from, again, probably go from 0 to 1. There's no reason not to use that. So y starts at 0 and ends at a, so it's just going to be at, and z is going to be a squared times t, or a t, what is it going to be? Let's think about that. So what we want is we want a parabola. So I guess it would be a t squared. So we can't just match the endpoints. It has to have a parabolic relationship. So when t equals 0, you get 0, which matches there. And when t equals 1, so I think it actually is not a squared. Well, I think it's the same result. I think it would be at squared. Because, yeah, that's a good question. Is it at squared or is it a squared t? And does it really matter? Because I'm thinking about if you were to go to a half, if t was equal to half, then you'd have 1/4 a squared. Yeah, so I think that's right. It's a squared t squared or at squared. I think I'll just call it a squared t. Okay, so hopefully we have in the book what it's supposed to be. Okay, so what we can do then is do our field vector of x, y, and z, but it's actually a function of it's a function of t. We'll make it a function of t. So the first function is z squared. So z in this case is it's a squared t squared squared times I. J is x squared, so we get plus a squared j, and then we would get the z component, or actually the last term is y squared k. So y is this, so you get a squared t squared times k. Okay, and then we have our position vector of x, y, and z, but we're going to do it in terms of t. So it's x of t, y of t, z of t. So you have so you have a I plus a tj plus a squared t squared k. And then you take the derivative of that with respect to t, and this goes to 0, so you'd have 0I plus aj plus 2a squared t k. So these are all with respect to t. So when you take the dot product, what do you get? Well, you have 0I here, so there's no I. You have a times a squared, so that's going to be a cubed j. And then you multiply here 2a squared t by a squared t squared. So that's going to be plus 2 a to the 4th t cubed k. Oh, but you don't have the j's and k's because it's the dot product. Okay, so we get a cubed plus 4a to the 4th t cubed. And then we're going to integrate from t equals 0 to t equals 1 of a cubed plus 2a to the 4th t cubed dt. And if you integrate a cubed dt, you get a cubed t. And if you integrate t cubed, you get t to the 4th divided by 4. And we evaluate that between 0 and 1. So we get a cubed plus 2 a to the 4th over 4. So let's see if they've got anything here in terms of. So this is C4. So when they do that, let's see. Just looking at the solution, and it's not exactly what they got. So let me just pause a second. Okay, well, I was thinking things were wrong, but I don't think they are wrong. It's just the solution in the book actually made a mistake, but made a couple of mistakes. But I think I've got it figured out now. Okay, so we're moving on to curve. What are we going to do next? So we did 1, 4, 3. So curve 3. So that goes from a comma a comma a squared to 0 comma a squared. So we get x is equal to, let t go between 0 and 1 again. So we have 1 minus a, 1 minus a minus, what is it, a minus at or something like that. So we start at a, and we subtract minus at. So when t equals 0, you get a for x, and when t equals 1, you get a minus a, which is 0. And this is a linear equation, so I think that works. You get y is equal to a, and you get z is equal to a squared. So there's a constant. So the field vector of x, y, and z is going to be equal to, I've already forgotten what those equation is. Got too many things open here. Maybe. Okay, so we've got z squared. So z is the first one. So you've got a squared I plus x squared, a minus at squared times j, plus k, which is y squared, so we get a squared k. And the position vector is going to be a minus at I plus a j plus a squared k. And if we take the derivative of that with respect to t, you'll get negative a I, and that's 0, and that's 0. So we need to do the dot product of f dot r prime. Let's see what we end up with. So there's no I and j components, and then you multiply a squared squared times negative a, so you get negative a to the 5th. And since it's a dot product, the vectors don't turn out. And so the integral is from 0 to 1, t equals 0 to t equals 1, of negative a to the 5th dt. So you get negative a to the 5th t, evaluate between 0 and 1, so you get negative a to the 5th. So that's the result of the third line integral. And then we have curve, what's the next curve? We're calling it curve 2. So that's from 0 comma a squared to 0 comma 0 comma 0. And in that case, x equals 0, y is equal to, and let's let t go from 0 to 1 again. So we're going to have 1 minus t times a. So you can see when t equals 0, you get a. So this is t equals 0 right here. And t equals 1, you get 1 minus 1 times a. So that's 0. And the same kind of deal with this other one. You'll have 1 minus t squared times a squared. So when t equals 0, you get 1 squared times a squared, which is a squared. When t equals 1, you get 0. So our field vector, so we've got z squared, so it's 1 minus t squared, a squared, squared times I plus x squared j, x is 0, so you get 0 squared j, plus x squared or y squared k, so you get 1 minus t a quantity squared times k. Now our position vector is going to be equal to 0I plus 1 minus t a j plus 1 minus t squared a squared k. And when we take the derivative of that, so we get r prime of x, y, and z. So this goes to 0. The derivative of this with respect to t is negative a, so we get negative a times j. And here we would get negative 2. Okay, so the 2 comes from the exponent. You get a negative sign from the negative t. So that's where negative 2 comes in, times 1 minus t to the first power times a squared k. And so that's r prime of x, y, and z, negative aj minus 2 times 1 minus 2a, I guess. Negative, we can make it positive, positive 2a squared times t minus 1, so this negative sign switches those around. Okay. And then we do the dot product of these two vectors. So there is no I component. The j here, this is 0, so there's no j component. The only thing we have is the k component. So we have 1 minus t times a quantity squared times, well, let's change this back, because then we can put the negative sign back here. 1 minus t. Okay, so we have negative 2 times a squared times 1 minus t. So that's the k component of r prime, and this is the k component of f. So let's see what we can get here. You're going to have negative 2 a to the fourth, because you a squared, negative 2, and then you have 1 minus t cubed. Okay, so we're going to integrate from t equals 0 to 1 of negative 2 a to the fourth times 1 minus t cubed dt. And if we let u equal 1 minus t, du equals negative dt. Actually, it's, yeah, that's right, negative dt. So this becomes, and let's see, when t equals 0, u is equal to 1 minus 0, so that's 1. And when t equals 1, u equals 1 minus 1, which is 0. So we integrate from 1 to 0 of, and let's factor out negative 2a to the fourth. And then we have u cubed times negative du from here. So we get negative 2a to the fourth, u to the fourth. This negative comes out front, becomes positive from the du, divided by 4, evaluated between 0 and 1. Okay, now this, at 0 you get 0, so, and then you subtract the lower limit, so you'll have negative a to the fourth times 1 to the fourth divided by 4, so that becomes negative a to the fourth over 2. And if we go back do our second integral, hopefully we ended up with, yeah, right there. So here we have a cubed plus a to the fourth over 2. So all of the parts put together, all together now. So curve 1 plus curve 4 plus curve, whatever the next one was, 3 plus curve 2. So curve 1 was 0. Curve 2 is a cubed plus a to the fourth over 2. Curve 3 was negative a to the fifth. And curve 2 was negative a to the fourth over 2. Well, those cancel out, and you end up with a cubed minus a to the fifth. And that's what they got in the book. They have a cubed times 1 minus a squared. So that is the line integral. So now we can do the curl. So our surface is this equation given by negative y squared plus z equals 0. That comes from z equals y squared. Okay. So first we need to find the curl of f. So to do that, we take I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, and the x component of the field vector is z squared, and then we have x squared, and then we have y squared. So our I component is going to be the partial of y squared with respect to y, that's going to be 2y. Partial of x squared with respect to z, that's 0. Then we subtract j. Partial of y squared with respect to x, that's 0. Partial of z squared with respect to z, that's 2z. And so we, and it's minus. So this is minus 2z. And then we have plus k. Partial of x squared with respect to x, going to be 2x. And minus the partial of z squared with respect to y, which is 0. So we end up with 2yi plus 2zj plus 2xk. So that's that's the curl. Now the unit normal vector, let's pause for a second because I gotta go back and look. So what we do is we go to this equation here for the surface, and we take the gradient, we'll call this capital G. G of x, y, and z is going to be equal to, actually that's, G is not a vector. So it's going to be equal to negative y squared plus z. And to take the gradient of g, you take this, the partial of this with respect to x, which is 0, so you get 0i. Then you take the partial with respect to y, which is negative 2y. So this becomes negative 2y times j, and the partial of that, this with respect to z is 1, so you get 1k. Now you have this ds that you need to change to dA, and you know, this is not the unit normal vector. I'd have to divide by the magnitude, but you know, they end up canceling out. The the magnitude of this thing is the square root of 1 plus g sub x, and this g thing is is this equation, is y squared. So you'd end up, so this is the small g, not the big G. The big G is where everything's equal to 0. So you take the partial of these with respect to y of xy and you square them. So you end up with 1, and the partial of this with respect to x is 0. The partial with respect to y is 2y, and you square it, and so you get the square root of 1 plus 4y squared. So that's what you would divide this by, but then convert these, you multiply by that same quantity. So they cancel out. So all we have to do here is, so we have the double integral, and in the xy plane, we go from 0 to a and 0 to a. So it goes from y equals 0 to y equals a, and from x equals 0 to x equals a. And then what we're doing here is we're doing the dot product of this curl of f with that. So if you do that, you'll get these j components together. So you get negative 4yz. And then if you do the k components, you get 2x times 1. So that's just 2x plus 2x times dy dx. But I've got z here, so I have to go back to my equation. Z equals y squared. So z equals y squared. So you go from 0 to a, and you go from 0 to a, and you get negative 4x y squared plus 2x times dy dx. And let's see if that's what they have. They got the opposite sign. So why does that happen? Is that right? No, that's right. Oh, wait a second. No. It ends up being that way. Yeah. So you first integrate with respect to y. So the integral of this with respect to y would be negative 4x y cubed over 3. And the integral of this with respect to y is going to be 2xy, evaluated between 0 and a. And then you multiply that whole thing times dx. So plugging in that, you get 4a cubed over 3 plus 4x, let's fix that. So you get negative 4a cubed x, negative 4a cubed x over 3. And here we'd have 2x times a, the integral from 0 to a, x equals 0 to x equals a, dx. And so if we integrate, well, you can see I can factor out negative 4a cubed over 3 plus 2a, that whole thing times x. So I can just leave that inside there. So I get 0 to a. So you get negative 4a cubed over 3. This doesn't seem like it's going to work out right, but so let's pause here for a second. It's going to really pause. Actually, really pause. Okay, yeah, so I see a mistake here. So this is 2y. So this should be 2. This should be 4yz. And so when you plug, you get negative 4y cubed. So when z equals x squared, you get negative 4y cubed plus 2x dx dy. Okay. So let's just ignore what I just did earlier. So you get the integral from 0 to a. So the integral of that would be negative 4 y to the fourth over 4 plus 2xy evaluated between 0 and a times dx. So these cancel out. You plug in a, you'll get a to the fourth plus 2xa all times dx. Now integrate with respect to x, you get a to the fourth x plus 2x squared over 2a evaluated between 0 and a. So the lower limit you get nothing, and you get a to the fourth times a plus these cancel out, which is going to be I must have missed a sign here somewhere. Yeah, there's a negative sign there. Forgot, so that's negative. So that's negative. Integral of x squared. Oh, I already did the integral. So you put a, so you'd have a cubed over nothing. So what you end up with is negative a to the fifth plus a cubed, which is a cubed times 1 minus a squared, which is the same as we got in the first one. How about that?